So energy balance, essentially, in this particular part, we're going to be, we're going to still carry the black box approach in our mind, right? Same thing here is mass flow coming in. In this case, sometimes heat is added and then work is done, right? Based on what heat is added and the properties of the inflow, the inlet condition, what can be produced or it may actually be added, right? And then you now have an exit stream, of course, right? It can be multiple inlets, multiple outlets. But for this set of slides, we're going to focus on, let me zoom this out so things are not cut in. Let me see if I can get this bigger. Okay, good. I can do better. Okay. I can still do better. 85. All right. So in this section, we're going to consider two types of control volume systems, right? We're going to do the vapor power cycle, and we're going to do the vapor compression cycle. So basically, the Rankine, the vapor power cycle is essentially a Rankine cycle, and it's the principle by which things like steam power plants operate on the Rankine cycle. And then we're going to look at the Rankine cycle with reheat to see, understand what happens when we have to reheat while we're trying to get stuff back in the turbine. And it's pretty much a straightforward reason why we do that. We're gonna talk about that. And then the vapor compression cycle essentially is the basis for operation of the refrigeration process. So they just call it the refrigeration cycle, right? And I think the major difference is that in this one we're dealing with an evaporation unit compared to the other one. Okay, where I think we just have a condenser and then we have a pump and a throttle valve. Okay, so we're going to go deep into that. What happens is these two systems are a combination of different units: condensers, turbines, pumps, compressors, and then we have to actually analyze everything as one single control volume. So we have an inlet coming from one unit into the other unit. Once we know what the outlet of that previous unit is, that's our inlet, and then we just focus on now the system that inlet is going into. We solve everything about that, and then we keep going around the units. Okay, so they will be solved independently, and in addition, energy can now move through the boundaries of the system, unlike the previous things we've been looking at, right? So first of all, we have to understand, okay, is mass balanced? Make sure that mass is balanced for your system between the control volume, and then we now understand what is the transfer of heat or work done across the boundary of the control volume. Okay, so for the purpose of this, we're going to be considering mostly steady state flow conditions, just like in the previous case, and we'll go through the derivation of the energy balance very quickly, and we're going to stick with kilowatts, right? Units of power. And this is because things are flowing, right? What is the definition of power? Power is work done divided by time, or energy divided by time. So it makes sense that if we're dealing with mass flow rates, right, things are not going to be static. It's not a batch process. So it makes sense that to unify the units between all these quantities, we want to just go with the power units, kilowatts, right? Okay. So the control volume indicates that there's no boundary work done by the system. And typically we have shaft work, such as with a turbine, compressor, or pump. Compressor or pump do the same thing, right? They compress. They add pressure to the system. All right? Okay, so the basic mathematics is consider a control volume, and mass will be flowing, and you consider mass as a rate now. We're going to be dealing with rate because it's flow. So M equals to rho VA, where rho is density, V is velocity, and A is area. Okay, there are some fundamental problems I've seen where the easy solution is just what's the mass flow rate of this in the system. You just look for what is the density, get your velocity out of the system, and then multiply by the cross-sectional area by which the mass is flowing, right? So if you're given volumetric rates, then you don't just A times velocity is the same thing as volumetric rate. All right, so these are the definitions of what I just mentioned now, and mostly in this chapter people like to deal with specific volume, specific dates, because we know that everything, we don't need to keep carrying all those 1,000 pounds of mass of this and that. You just solve everything in terms of a specific quantity, and then when you're done, you now multiply things through, right? To now get what your final answer should be. So that's kind of how most of these energy balances and thermodynamic problems are solved.